Okay, so in this problem, you're basically finding the slope. And we're used to the slope being easily deduced, but in this problem, we have to use implicit differentiation. So let's read the problem. Find dy dx given the equation such that x squared plus y squared is equal to 50, and the slope is set at x equal to 3 and y is equal to 4. Here's a more better view of the expression we're given. And if you don't remember performing implicit differentiation, that's okay, we can do review. So let's say we have to take the derivative of x cubed with respect to x. We know for a fact that's 3x squared with the power rule. Now what if we have to take the derivative with respect to x, but there's only y? We still have to apply the power rule to y, but we have to leave in the dy dx expression. And if it's some obscene variable, we still have to apply the power rule, and you'll notice that there is no other expression for 3x squared, and that's because it's dx over dx compared to dy over dx and dg over dx. So I'm sure you recognize a pattern here, and at this point it's kind of counterintuitive to put in dx over dx, so we can just negate that. So we got a review out of the way. Let's actually find dy over dx. So what's the first step towards achieving that goal? Let's multiply the whole system by dy over dx. So it's going to look like this, and we're going to differentiate both sides. So the derivative with respect to x of x squared would be 2x, and we're going to implicitly differentiate y squared. And what is the derivative of any constant? If you said it's 0, you'd be correct. So this is our result, and now let's try to isolate dy over dx. And what that looks like is we first subtract 2x on both sides, then we'll have to divide by 2y, and you'll notice that this expression is technically finished, but we can simplify even further. And we can do that by just simplifying, getting rid of the 2's. And that is our slope, our rate of change actually. But are we really done? What else is there to do, really? We have the slope, and we have to find dy dx at a given point. And as a result, we just have to plug them in. So at the point 3, 4, our slope is negative 3 over 4. So graphically speaking, the slope's going to be at a decline. Alright, so this problem is going to require plugging in a specific point for dy dx. We're actually just going to solve it. So that's great. We can now begin by differentiating both sides. So that's when we differentiate both sides. On the left side, the 5 is 0, negative 2x, negative x squared will be negative 2x. And we have to differentiate cosine of xy squared. So to do this, think of applying chain rule as a funnel. You start from the largest and you funnel it down to its smallest components. So what that means is you take the derivative of cosine, which is negative sine of whatever is within the parentheses, and after that you apply the product rule for x times y squared. And yes, we are still going to have to include the dy dx as a means of implicit differentiation. So once we do that, instead of adding sine of xy squared, let's actually distribute it so we can get rid of brackets. So this is what we got. What would our next step be? Well, we can actually add y squared times sine of xy squared. And all we really need to do is divide by negative x 2y sine x squared. And there we go. That's how you form. That's how you find dy dx through implicit differentiation and applying the chain rule. Sometimes when you're doing implicit differentiation, you may not always be asked to find dy dx. Sometimes it might be the second derivative you have to look for. So we have this expression x to the fourth plus y to the fourth is equal to 7. Let's differentiate both sides. And you'll see here that we get 4x cubed plus 4y cubed times 2y dx, which is equal to 0. And we're going to subtract 4x cubed, and then what's next? We divide by 4y cubed. The fraction can be simplified to just negative x cubed over y cubed. And I usually don't leave my answers as fractions, especially when I have to solve for the second derivative. I just write it as negative x cubed times y to the negative third power. And this helps me because most students are more familiar with the product rule than the quotient rule. And in this step, we can apply the product rule instead of the quotient rule to find the second derivative. So when we differentiate again with this expression, the product rule still applies, and the concept of implicit differentiation is also upheld. Notice here that dy dx is still equal to the prior expression we solved. Now that we have the second derivative set up, let's plug in the points that we need, 1 and 2. So, yes, substitute dy dx, and you plug in your values. Go ahead and pause a bit. We'll get to math. It's going to be a fraction. You should get something a little like this. We have negative 3/8 minus 1 over 28. And you're more than welcome to simplify into one fraction by multiplying the negative 3/8 by 16 over 16. And that should be it for solving this expression.